Okie doke. Okay, the next section deals with nomenclature of epoxides. And as far as nomenclature goes, this is some of the most challenging nomenclature that we look at in all of organic chemistry. And the reason why is because an oxirane can also be referred to as an epoxide. So it says here, for cyclic ethers, the size of the ring determines the parent name for the molecule. If you only have 2 carbons and 1 oxygen, then it's an oxirane. If you have 3 carbons and 1 oxygen, it's an oxetane. 5 carbons and 1 oxygen, it's an oxalane. And 5 carbons and 1 oxygen, it's an oxalane, or oxane, excuse me. We're not really going to worry about oxetanes, oxalanes, and oxanes a whole lot. And in fact, you probably recognize this compound. This is THF. And you saw that when we had a second oxygen in here, we called that dioxane. Anyhow, that's neither here nor there. But right now, we're going to talk about oxiranes, which are also known as, so AKA epoxides. And we're going to talk about how to name these. So let's get into it. It says an epoxide can have up to 4 R groups. So if you're wondering, like, why do you have 2 names, Mr. Dion? Well, when I'm referring to just the 3-membered ring, that I call that oxirane. Okay, that the name of this molecule is oxirane. And if I have, a substituent on an oxirane, then I can name that as a substituted oxirane. But I can also view it from the point of view of the longest carbon chain, and it's like a functional group coming off of the carbon chain. In that case, I call it an epoxide. So oxirane or epoxide. And that will become more clear as we move along. So we can have substitution on our oxirane. We can have up to 4 R groups on it. And the simplest possible epoxide is ethylene oxide. So just this compound, besides calling this oxirane, we can also call it ethylene oxide. All right, and you need to know ethylene oxide as well. You should know that name. Even though epoxides aren't all that stable, they are found in nature. You can see this pheromone of a moth. It has an epoxide in it. And also in this really crazy compound, periplanone B, it's got 2 epoxides in it. How would you like to try to synthesize that thing? Oh, yeah. Anyhow, it looks like a pretty tough molecule to me. But anyhow, I digress. Well, let's move on from there, and let's talk about the rules for naming epoxides. It says there's 2 methods. The first one is that you treat the oxygen like a side group, and you use 2 numbers for its locants. So in this example here, you've got 3-ethyl-2-methyl 2,3-epoxy pentane. So in here, of course, they're treating it as an epoxide. So they find the longest carbon chain, 1, 2, 3, 4, 5, and they say, okay, well, this group coming up here to the oxygen and coming down, this is a 2,3-epoxy. Okay, and the other groups are just a methyl and an ethyl. Not too bad. You can also name it as the 3-membered ring. You start with the number 1 always on the oxygen because oxygen has a higher atomic number than carbon. So we would go 1, 2, 3. The reason they're going to 2 here is because you have ethyl groups which are larger than methyls, and so they're going to take higher priority over the 2 methyls. So you have a 2,2-diethyl, 3,3-dimethyl oxirane. Again, we're just looking at the oxirane ring as the parent of the entire thing. That's it. That's all I think I have for the rules. And you might be thinking, oh, jeepers, that's it? And it's that complicated? Well, let's try a couple of them, and then I'll give you some time to work on some other ones before class on Wednesday. Let's take a look at these 2 here. They're kind of similar. First, let's name it as an oxirane. So we'll name it as an oxirane, and we'll use red to name it as an oxirane. So if I name this compound as an oxirane, this is going to be number 1. This carbon will be number 2, and this will be number 3, right? An oxirane, remember, is just a 3-membered ring. 1, 2, 3. The reason I'm giving this carbon number 2 is because it's the one that's got substituents on it, and I want to give those substituents the lowest possible number. And so I would simply call that 2,2-dimethyl oxirane. So let's scribble that down. 2,2-dimethyl oxirane. Now we're going to try naming it as an epoxide. So what we need to do is find the longest carbon chain, and that longest carbon chain has to contain the epoxy group in it, right? Going from carbon to oxygen and back to carbon again. Well, let's zoom in here and let's find the longest carbon chain. You can see the longest carbon chain has 3 carbons in it, 1, 2, 3, like this. And you could have gone 1, 2, 3 like this, you still get the same answer. So 1, 2, 3, and we have the oxygen, and then we also have a methyl. Well, we want to give the epoxy priority over just a plain old alkyl group. So we would number this as 1, 2, 3, and thus, blue, so 1, 2, 3. So this would be a 2, I have a 2-methyl, and then I have a 1,2 epoxy propane. So let's do it like that. So I have 2-methyl. So 2-methyl, 1,2 epoxy propane, like that. 2-methyl, 1,2 epoxy propane. All right. And remember that the epoxy is a side chain on the R group. So we always tack it on to the R group, to the parent chain. I'm going to skip the next one, and we'll do this one at the start of class on Wednesday. Let's try these ones here. Let's try a couple of these. These are trickier because there's stereogenic centers in them. Let's start with, I don't know, let's start with this one on the top, I guess. And we'll start by naming it as an oxirane. So we have our oxirane, which is our 3-membered ring here. We've got number 1 would be here, number 2 would be here, number 3 would be here. So I've got a 2-methyl and a 2-phenyl. M comes before P in the alphabet, so we'll call this a 2-methyl 2-phenyl oxirane. And then we've got to figure out what the stereochemistry is. Is it R or is it S? So let's zoom in here and see if we can figure this thing out. So this is our stereogenic center right here. So this is going to be our highest priority group, the oxygen. The methyl would be our lowest priority group. Then if you look at this carbon, it's attached to carbon, carbon, carbon. And this carbon is attached to an oxygen, a hydrogen, and a hydrogen. And thus this would be our tiebreaker. So we go from 1 to 2 to 3. So we're going clockwise, and thus the stereochemistry here is R. So we have an R2-methyl 2-phenyl oxirane. The good news is that the stereochemistry isn't going to change when we try to name it as an epoxide. So now we're going to erase all this spinach, and let's name it as an epoxide. We find our longest carbon chain. We want to give the epoxy group priority. So we have 1, 2, 3, like this. We've got a phenyl at carbon 2, and we've got a 1,2 epoxy propane. So that means that the compound would be R again, 2-phenyl, 1,2 epoxy propane. All right. Let's try one more, and then we'll save the last one for class on Wednesday. So we're going to do this one as an oxirane again. This would be priority number 1. A propyl group has higher priority than an ethyl. So we go from 1 to 2 to 3. And so this is a 3-ethyl, 3-ethyl, no, sorry. I think here. Yeah, it's a 3-ethyl 2-propyl oxirane. So yeah, I've got that labeled right. So let's see here. We've got 3-ethyl 2-propyl oxirane. And now we need to figure out the stereochemistry of both stereogenic centers. So we've got 2 something and 3 something. So is it R or S? And then is it R or S? So let's figure this out here. Let's start with number 2, I guess. Doesn't matter. We'll start with this stereogenic center here, which is number 2. Okay, so let's do it a little bit quicker this time. We have a hydrogen atom going in back, so that's good. That's our lowest priority. This is our highest priority. This carbon is attached to oxygen, carbon, hydrogen. This carbon is attached to carbon, hydrogen, hydrogen. So this would be our tiebreaker. Therefore, we go from 1 to 2 to 3. So we're going like this, which is clockwise. So it's 2R. And then for the second stereo center, let's highlight that one. So we'll put this here. This is our highest priority group. We have our hydrogen coming out in front. So whatever we get, we're going to reverse it. This is our 4th highest priority. This is 2. This is 3. And so we go from 1 to 2 to 3 like that, which is counterclockwise, but we reverse it in this direction. So this is also R. So there you go. We've got 2R and 3R, 3-ethyl, 2-propyl oxirane. Now we're going to name it as an epoxide. And so we find the longest carbon chain, and we want to give the epoxy the lowest possible locate number. So we have 1, 2, 3, 4, 5, 6, 7. So this is some kind of 3,4 epoxy heptane. And what else? We have 3R and 4R, 3, 4 epoxy heptane. Son of a gun, I just lost everything. So we have 3R and 4R, 3, 4 epoxy heptane. There we go.
Can I ask you a question really quick?
Go for it.
So on 13.7, the first 2 examples the first one that you did.
Mm-hmm.
When you counted them,
mm-hmm.
When you showed us the epoxy the first time on 13.7 when you were going over nomenclature, it starts out as counting them like 1, 2, 3 from over. But on the example that we were given, you started at 1 from like the left corner. I would have started 1 from the right corner, just judging from the example that you gave us. So why did you start at 1 right next to it? Does that make sense?
So
yeah, the one that you're on right now, the top right. Yeah, the top right. So yeah, I know that it's counting the longest carbon chain, but then on the example that we were given, like the slide below this, I would have started 1 on the right hand side, but you started 1 on the left, just judging from that example. So why is it switched? Is it just because it needs to be closer to the epoxide?
No, it's not switched. So here you find the longest carbon chain, and you want to give the epoxide the lowest possible numbers. So here it would be 2 and 3. And when I named it as an epoxide, what I did was that I started here, 1, 2, 3. Because 1 and 2 are lower numbers than if I started over here, 1, 2, 3. Then it would have been 2, 3. So I want to give the epoxide 1 and 2. So that's why I number it 1, 2, 3. And this would be 2-methyl, 1, 2, 1, 2, epoxy propane. Does that help?
Yeah, no, that does. Thank you.
Yeah, no problem at all. All right. There we go. So if anybody can figure out the mystery of why there's something that I touch on my iPad and it just deletes everything that I've done. So it didn't delete what I recorded before. Anything that I just wrote down since we started this lecture, it's all gone. And I don't know why it does that. It's just like there's something that I'm touching and it just erases everything. So student asked me, like, why don't you post the annotated slides? It's because I end up losing a lot of what I write down will be erased instantaneously for some reason. Anyhow, let's see here. So section 13.8 deals with preparation of epoxides. Again, on Wednesday, we're going to take a look at some more nomenclature examples, but I want you to give it a shot before we tackle that in the next class. So it says, recall that you can make an epoxide using a peroxy acid. And the two most common peroxy acids that we see are MCPBA and peroxyacetic acid. Those are the two that we see in this class. And normally, when we use peroxyacetic acid, of course, in Organic Chemistry 1, we would take the epoxide, treat it with aqueous acid, and we would end up with, we'd always end up making a transdiol that way. But now we're not interested in making a transdiol. We're talking about epoxides and how do you make an epoxide. So this is how you do it. You treat it with MCPBA. But what's interesting about this reaction, and something that we didn't discuss in the alkenes chapter, is that epoxidation with MCPBA is a stereospecific reaction, meaning that if you start with a cis alkene, when you form the epoxide, you end up with your two R groups on the same face of the molecule. They're cis. And if you start with a trans alkene, you end up with an epoxide where the R groups are on opposite side, namely you get a trans isomer. So stereospecific, not stereoselective for one over the other, but stereospecific. It favors one over the other. Well, you might be wondering, are there other ways to make an epoxide besides using MCPBA? I'm glad you asked. There is another way to make an epoxide, and an epoxide can be synthesized from a halohydrin. And hopefully you remember hydrohalogenation. And hydrohalogenation is when we take an alkene and we treat it with bromine in water as a solvent, and we end up adding a bromine and a hydroxyl. Well, what happens is if you take that halohydrin and you treat the halohydrin with sodium hydroxide, you end up forming an epoxide. What's cool about that is that you have to have the hydroxyl pointing up and the bromo pointing down in order for this chemistry to work. If you try to do this reaction, or if you were to try to do it with the hydroxyl going up and the bromine going up like this, and you treat that with sodium hydroxide, you get no reaction. Nothing happens at all. So they have to be trans to one another in order for it to work. Let's take a look at why that is. What happens when you make the epoxide from a halohydrin is in the first step, your hydroxide from the sodium hydroxide deprotonates the alcohol to make the alkoxide. But since the oxygen, or the bond between the carbon and the oxygen, is pointing up like this, and the bond between the carbon and the bromine is pointing down, they are anti-periplanar to one another, and they have to be in order for this SN2 reaction to work. This is nothing more than an SN2 mechanism. You have your nucleophilic attack here, and you have your loss of leaving group over here. But again, they have to be trans to each other in order for that to occur and form the epoxide. If we were to draw the six-membered ring like this, let's say, and if the groups were cis to one another, so let me try to draw the ring a little bit better, that would mean that the alkoxide would be pointing up like this, which is great, but then the bromine would be up and equatorial. And that would mean SN2 cannot occur. Kind of cool. So they have to be trans to one another. Again, to review, you do nothing more than take your halohydrin and just treat it with sodium hydroxide, and you end up making an epoxide. And this is a mechanism I expect you to know. So let's put that in here. Know this mechanism. Very important. All right. Must be trans for the elimination to occur. Let's scribble that in here too. Put must. What do we put? This. We'll put alkoxide, and bromine must be trans for SN2 to occur. There we go. A little more detail. Cool. So now we've got two ways to make an epoxide. Let's review. We can either use MCPBA or we can use halohydrin formation followed by treatment with sodium hydroxide. And what's cool is that no matter which one of these reactions you pick, they're both stereospecific. If you start with cis, you get cis. If you start with trans and you do either of those, you end up with trans. Doesn't matter. It is stereospecific. Well, with all that information in mind, let's take a look at a practice problem here. Question 13.13 says, identify reactants that you would use to form a racemic mixture of each of the following epoxides. First thing I notice is in the first one, you've got one aromatic ring going back and you've got the other one coming out in front. So the two aromatic rings are trans. Thinking about that in terms of retrosynthesis, that would mean that whatever my alkene is, I'm going to have one phenyl group going in the back, and I'm going to have the other phenyl group coming out in front. So you see that on the side that's got this phenyl ring that's pointing out, you also have this hydrogen. That means you're going to have a hydrogen out here. And the side that's got the phenyl ring going back, you've also got a methyl. So that means you're going to have a methyl group coming out here like this. And now we've identified the starting alkene that you would use to do the synthesis. Therefore, you start with this compound and you would treat it with, MCPBA, or you could use the two-step method, which is to first make the halohydrin using bromine and water, and then following that up by treatment with sodium hydroxide, and that is going to give you the product. There we go. Let's try another one. The next one, we're going to do retrosynthesis again. The carbon-carbon bond, where our double bond is going to come from, is this bond. So we know we're starting with an alkene. Why don't we draw the groups that are going in back, and we'll put them up here. So here's one group that's going in back. It's a cyclohexyl, and on the other side, you've got a hydrogen. So we'll put the cyclohexyl up here. Oops, it's not a very good cyclohexyl. There we go. And then we've got our proton up here. And then we'll draw the groups that are coming out in front. We've got a hydrogen on the left and a methyl group on the right. So let's put the hydrogen on the left and we'll put the methyl group on the right. And there you go. Done. There's our starting alkene. And we're going to do the same old reaction conditions as before. So we'll just copy and paste that. Copy and paste. And this won't work either, but anyhow. Yeah. There we go. All right. And then the last one is kind of neat because you have this ring that's attached to the one carbon of the ring of the epoxide. But this is the carbon-carbon bond where our double bond will come from. So let's take a look at that. And then we're going to have this five-membered ring. So we have 1, 2, 3, 4, 5. Like that. And if you count over from here, you go 1, 2, 3. Then you have the oxygen. So we'll go 1, 2, 3. So here's our oxygen right here. Maybe I'll put it in black. I want to be somewhat consistent. And then in the back, you have a hydrogen atom going out here. And then you have a methyl group coming in front like that. And again, same old reaction conditions as before. So we'll just put an arrow and we'll put ditto. Give me a thumbs up if you follow me on these retrosyntheses for determining what the alkene that would be as a reactant to make any of these epoxides. Are there any questions about that? And don't hesitate to stop me. It's no problem. That's why they pay me $3.50 an hour. Anybody? Okay. All right. Let's move on. Give me a thumbs up. Does anybody follow me on that? I can't see.
Honestly, I mean, I don't really want to bother you, but if you could
You're not
go
bothering
one
me.
of them like slower, I'm following you, but like you're doing it very quickly.
Okay.
And I'm a little lost. I'm following you a little bit, but I'd like to just to see it, if you don't mind, like how you drew it out, but like each step of like, because if I were to look at a problem like this, I don't know if I would be able to break it down as easily as you did.
Yeah, so you've got to be able to manipulate the shapes in 3 dimensions in your mind. Right? This goes all the way back to chapter 5 in the stereochemistry chapter. Let's imagine that your eyeball was looking down. Okay, if you were looking down on this molecule, right, looking down this way, what would you see? What your eyeball would see is you would see the oxygen atom, right? And then you'd see a bond going this way and a bond going that way, right? You've got the 3-membered ring. So I'll try to draw kind of slightly at an angle like this, okay? So there's your 3-membered ring. Are you with me on that? So what I'm
Yes.
drawing is this, but you're kind of looking at it from the top, okay? So you've got this cyclohexyl going in the back. And if it's going to the back, that means that when you're looking down on this, it's going to be going to the right-hand side. You're going to have the cyclohexyl coming off over here, and then you're going to have the hydrogen coming out over here. Does that make sense?
Yes.
Okay, so you have the same thing on the other side, right? You have the hydrogen going in the back, and then you have the methyl group coming out like this.
Okay.
Okay, so then all I did was manipulate that shape in my mind's eye and say, well, what I have to start with is an alkene to make this epoxide. All I do is delete these parts and I say, well, if I put a double bond here, there you go. That's the alkene that you would need. Right? The main thing
Okay.
is that you have all the groups in the correct orientation. Because if you drew this, if you had the cyclohexyl group over here, let's say, and then you put the methyl group up here and had the hydrogen and had a hydrogen, that is it. The connectivity is correct, but the stereochemistry is wrong. So that would give you the wrong answer. Okay. So we can do the same thing with the last one, a similar treatment. Take this. Now let's put this over here. Oops. So we can put this here. And we do the same kind of thing. Imagine your eyeball is looking down from the top onto this molecule. What would you see? You'd see the oxygen, and then you see a bond going down. Let's just make it a very slight angle because you're right on top of it, right? And then in the back, you see that's this bond, what I just drew coming off of there. Right, so you've got that bond to go into carbon 2 that I have labeled. Then you have to 3, then you have to 4, like that, and then 5, and then you have something that looks like that. And on the other side, if I have a bond going up and a bond going down, the bond going up, Lindsay, would that be attached to the hydrogen or the methyl?
Hydrogen. Or
Exactly.
no. Oh yeah, okay. All right.
Yeah, because it's going in the back, right? Everything that's going in the back is going to be on, if you're looking down, going, and you're standing like looking this direction, it's going to be on the right-hand side. So you've got the hydrogen here, and you've got the methyl group down here. So there's the epoxide looking at it from the top. So you do the same thing. You erase this, and you say, this would be my starting alkene. Right? And this one, if you tried to draw this, and if you said, okay, well, it doesn't matter where I put that oxygen. I'll just put a 5-membered ring coming off of here, and I'll just put the oxygen wherever because it doesn't matter. And then I'll do this. That would be wrong. You'd get the wrong isomer because you'd have the oxygen in this position instead. And so that's the technique. That's how you solve this problem.
Oh, thank you. Wow.
No problem. All right. So again, you might want to go back to chapter 5 and just practice, looking at things in 3 dimensions because it comes up a lot in the class. Anyhow, hope that helped. And let's move on. And so section 13.9 deals with enantioselective epoxidation. We're going to skip that altogether. I've never seen it show up on any kind of standardized test, so don't worry about enantioselective epoxidation. But now we're getting into something really, really heavy and really important. Kind of two heavy sections of this chapter. The first one was the nomenclature, and again, we're going to review that some more next class. But the last one, I'd say, is the ring opening of epoxides, because we're going to look at two different ways to open an epoxide. One way is with a strong nucleophile. So strong nucleophiles like Grignard reagents, hydrides, alcohols, alkoxides. And then we're also going to look at acid catalyzed ring opening. And you can imagine that since an epoxide is so highly strained, that three-membered ring, I mean, if you take a model kit and try to make a three-membered ring, with my model kit, it would break the models. So yeah, I don't even make them. But if you were to take a Grignard, which is a carbon with a negative charge, that's going to act as a nucleophile, and it's going to attack one of those electrophilic carbons, and it's going to open the ring like that. So you crack it open like a jack-in-the-box, so to speak. So then you have 1, 2 carbons. You'd have an alkoxide on one side, and then you're going to have an R group over here like that. And that is the mechanism for nucleophilic ring opening. Let's take a look at it in detail. It says strong nucleophiles react readily with an epoxide. Here's a hydroxide. Hydroxide is a really strong nucleophile. You have an epoxide. Remember that in the epoxide, there's two dipoles. There's a dipole going here, and there's a dipole going here. So both of those carbons are delta plus. This is delta plus. This is delta plus. But since it's symmetrical, you could draw the arrow to either one. It doesn't matter. And so we have our nucleophilic attack occurring, and this is like a loss of leaving group, so to speak, to make the alkoxide. So then what happens in the second step is that you treat it with water or mild acid, and that does a proton transfer. In this case, you end up forming a diol. So you end up with ethylene glycol in this case. Anyhow, if you look at the bottom, it says opening of the ring is thermodynamically favored. Why? Because the whole thing is so strained to begin with. It's ready to crack open. Like I said, like a jack-in-the-box, it's just ready to pop open. Take a look at the potential energy diagram for the ring opening of an epoxide compared to just a normal ether. Why are epoxides in this chapter? Because an epoxide is a type of ether, right? You've got an R group here, an R group here, and you've got an oxygen in between. But if you compare that to a traditional ether, this has ring strain, which is because the two R groups are separated by only one bond. And that means that their potential energy is going to be much higher than those of a normal ether. And that's why if you just take a regular old, dialkyl ether and you treat it with hydroxide, you get no reaction because the activation energy is much too high. EA is too high. But when you treat it with an epoxide, you see that the activation energy is much, much lower, and that's why the ring opening of the epoxide is thermodynamically favored. What are some compounds or some ions that we could use to open up an epoxide? We can use an alkoxide. We can use a cyanide. And cyanide is Cn minus. You can use a hydrosulfide. So this is, let's see here, hydrosulfide. So that's SH minus. You could use a Grignard, or you can use a hydride, like lithium aluminum hydride. Either way, all of those are good nucleophiles, and they're all going to react with an epoxide. Let's just take a look at one of the mechanisms for fun. We'll just take a look at the cyanide. Right, you've got that strained ring, the epoxide, and if you treat that with cyanide, cyanide is a strong enough nucleophile that it's going to come in, do a nucleophilic attack, the ring's going to open, and that's going to give you this compound after a proton transfer. All of them follow the same mechanism. However, it's important to note that all of these ring openings are regioselective and stereoselective. So we have to look at that now in detail to understand how that works. There's some really interesting nuances here. The first one is in terms of regioselectivity, and this one's not that much of a stretch. It says that in terms of regioselectivity, the epoxide ring opening is SN2. So what does that mean? If it's SN2 reaction, it's going to attack the least hindered carbon. You take a look at these two positions, the one highlighted in green and the one I'm highlighting in yellow. Well, the one that's highlighted in green is less hindered, and so it's going to undergo the nucleophilic attack. Your nucleophile is going to come in, it's going to attack this carbon, it's going to open up the ring, and you're going to form an intermediate that looks like this, where you have the two methyl groups. You're going to have your oxygen with a negative charge, and then you're going to have your nucleophile here. And then in the second step, you do a proton transfer. So you treat it with water, and then the alkoxide is going to grab a proton from the water molecule, like that. Kind of a neat reaction, because not only are you adding the functional group from the nucleophile, but you're also making an alcohol, 2 carbons apart. 1, 2, and then an alcohol. So that's our regioselectivity, but what about stereoselectivity? If the reaction is SN2, well, we know from Organic Chemistry 1 that SN2 reactions occur with inversion of configuration. That umbrella flipping in the wind, if you remember that, like an umbrella flip. Or put in more organic chemistry terms, if you have a wedge, it gets converted into a dash, and if you have a dash undergoing nucleophilic attack, it gets converted into a wedge. So we have our nucleophile, we have 2 carbons in our 3-membered epoxide ring, or oxirane ring. The nucleophile is going to take, nucleophilic attack will take place at the least hindered carbon, the one highlighted in green. Well, look very carefully at this bond. This bond is going up. It's coming towards you. It's coming out of your screen. And so when the nucleophile attacks, it's going to attack from the bottom face of the molecule. Attack from bottom. So if it's attacking from the bottom, before you crack open this bond like this, that means that your bond to the nucleophile is going to be on a wedge, or sorry, a dash, because it's pointing down. And there you go. So we get inversion of configuration during our SN2 reaction. So now we've covered the regioselectivity. The nucleophilic attack will occur at the least hindered carbon. And when we look at the stereochemistry, the reaction will always occur with inversion of configuration. Now we're going to switch gears and we're going to look at something different. So now let's write this down in the slides. Now for something a bit different. Because everything that we've been talking about up until now has been treating an epoxide with a strong nucleophile, like an alkoxide, like a cyanide, like a hydrosulfide, like a Grignard, like a hydride. Now we're not going to treat it with a strong nucleophile. We're going to look at something different. Now we're going to talk about the acidic or epoxide ring opening under acidic conditions. Think about it. Everything that we just talked about was taking a strong nucleophile and just reacting it with the epoxide. Now we're using an acid. So check this out. It says acidic conditions can also be used to open an epoxide with a weak nucleophile, like chloride, bromide, water, or an alcohol. And of course, the nucleophile from HCl would be chloride, bromide, and then water or an alcohol. So how is that going to work? Well, the first step is going to be a proton transfer onto the oxygen of the epoxide. And now that you've created this oxonium, what that's going to do is that's going to pull electron density to try to fill in that positive charge, and that renders these carbons even more delta plus than they were before. So now you have the carbons rendered even more electrophilic. And so now your nucleophile, even if it's not a strong nucleophile, can come in and do a nucleophilic attack, and we have the loss of leaving group occurring simultaneously. So now we open up our epoxide. There's no need to do a proton transfer at the end because we did it in the first step. And there you go. Now, there's some interesting nuances with acidic conditions. What are those interesting nuances? Well, there's some things that you might not even expect, but we're going to get to that in a second. It says here that water or an alcohol could be used as a nucleophile. If water is your nucleophile, again, after you do the proton transfer, you make your oxonium. If water is your nucleophile, it's going to come in and attack, and you're going to end up with a diol. However, if your nucleophile is an alcohol, ROH, well, in that case, it's going to do the nucleophilic attack, and you're going to end up with an ether and an alcohol in the same molecule. In fact, this first reaction that I have shown here, that's how ethylene glycol is made, which is used in antifreeze. This is how it's made on an industrial scale, is they take ethylene oxide and just treat it with a catalytic amount of sulfuric acid and water. So it's an acid catalyzed ring opening reaction. All right, now that we've got that down, I got something really interesting to show you. And that is the Regio selectivity of the ring, acid catalyzed ring opening. But before we do that, I guess we'll look at one more slide. And this is just the mechanism. And I'll put here, know this mechanism. Make sure you know this one. The first step is just the proton transfer to form the oxonium. And then water can come in as a nucleophile. You open up the ring, then you do another proton transfer. So not a very complex mechanism, but an interesting one nonetheless. With all that in mind, let's turn our attention to what I was trying to get at, which was the regioselectivity of acid catalyzed ring opening. So this is for acid catalyzed. Look, if we go back to just a plain old nucleophile, strong nucleophile, it was just least hindered carbon, attack, done. Now, when we're in acidic conditions, it's different. Check it out. It says, under acidic conditions, the nucleophilic attack rather, still occurs at the less substituted carbon when you have a primary and a secondary carbon atom present. We look at this epoxide. This carbon is primary because it's only attached to one other carbon. We look at the other carbon, this carbon is secondary because it's attached to two carbons. Well, when you have a primary and a secondary, the dominating effect is going to be sterics. Excuse me. And the nucleophilic attack will occur at the least hindered carbon. Nucleophilic attack occurs here, least hindered carbon. However, if you have a primary and a tertiary, the nucleophilic attack is going to occur at the tertiary carbon. If you're thinking, why the heck would it do that? It's because the dominant effect here is not sterics, but electronics. So we'll put here electronic effects. Dominate. And we'll put here steric effects. Sounds good. Effects dominate. Okay. Now, if you're wondering why in the heck would it attack at the more hindered carbon, that doesn't make any sense based on what you've learned in this class. Well, as you can imagine, there's a reason for it. And check this out. Here's the reason. It says since the epoxide is cationic under acidic conditions, right? When you protonate it, you have a positive charge on the oxygen. Remember that I told you that that positive charge sucks electron density away from both carbons in the ring? Well, if we think about the delta plus that can occur on either carbon, if you have a primary carbon and a tertiary carbon, which one of those is going to be more comfortable with a partial positive charge? The answer is the tertiary carbon is much more comfortable with that charge. And therefore, what that does is it weakens this bond greatly, weakens that bond a lot, so that the nucleophile is going to attack at the most hindered carbon because it's easier for the positive charge to pass through the more substituted carbon when it's tertiary. So the conclusion is this. If you have a primary and a secondary, the dominant effect is going to be sterics. But if you have a primary and a tertiary, and we'll put in here, or a secondary and a tertiary, either way, whenever you have a tertiary carbon, electronic effects are going to dominate. End of story. And that's it. So that's pretty interesting when you think about it. Yeah, well, let's move on from there and let's talk about the regioselectivity. And the same thing occurs after the proton transfer to make the oxonium. Once you've made the oxonium ion, wherever the nucleophile attacks, it's always going to attack on the opposite face from the epoxide. If we look at this molecule here, you see that the epoxide is pointing up. And since the epoxide ring is pointing up, it doesn't matter that the methyl is pointing down. Once it's protonated, the alcohol, which would be the nucleophile, is going to attack from the bottom face of the molecule, like this. If you draw the chair of the six-membered ring, it's going to look something like this, where you've got the epoxide going up, up. I'm trying to draw it the best I can, like this, okay? There we go, like that. And you have the methyl group, which is going down. So here's your methyl. But when your alcohol comes in as a nucleophile, since all of this is going up, the alcohol is going to attack from the back face of the molecule, or from the bottom side. And when that opens up, it's going to cause the methyl group to flip positions. So it's going to go from pointing down to now the methyl group would be up. The alcohol would be down here. So I guess it would be an oxonium as an intermediate, like that. And then we have our hydroxyl, which is pointing up. So again, these two groups, the hydroxyl and the methyl, are both pointing up like this. And then the OR would be pointing down. Either way, if you're like, I'm a little bit confused on this whole chair thing, the bottom line is what I'm trying to show you is that inversion of configuration is what's taking place here. So with all that information in mind, let's take a look at some practice problems of the ring opening of epoxides. So in this one, all we're doing, it says, for each of the following reactions, predict the product and draw a mechanism for its formation. So you can see that in the first one, we've got a thiolate. So when you have, a sulfur with a negative charge, a methyl group like this, that's called a thiolate, or it can be called a mercaptide. But either way, it's a good nucleophile. It's a sulfur with a negative charge. Here you have aluminum hydride, which is going to be a hydride delivery agent. So hydride is a good, excuse me, a good nucleophile from the aluminum hydride. And here you have an ethoxide. So all of these are good nucleophiles. And so there's no acid here anywhere in any of these problems. So what happens when the nucleophilic attack is occurring, it's going to be at the least hindered carbon. If I highlight this carbon in yellow and this carbon in green, which one of those carbons is going to undergo the nucleophilic attack by the sulfur, the yellow one or the green one? Could anybody tell me?
Yellow.
Absolutely, right? Just the less hindered one. So this is where mechanisms come in so handy because they enable you to see what's happening. The nucleophile is going to attack the yellow carbon. We break this bond. There you have it. So now we have, I'll start by drawing that carbon-carbon bond. So there you go, like this. Now on here, we've got a methyl group going down here. We've got the bond to the oxygen going like this. Okay. And attached to this carbon, which is this one right here, we've got the sulfur and the methyl group, like that. I'm just going to pretty it up here a little bit because what I drew is kind of ugly. Let's just fix that up. So we've got our MES, like that. Okay, so that's the first step. And then in the second step, you're going to treat it with water. And you're alkoxide is going to grab a proton from the water, and then you're going to end up forming this compound. I get alkoxides on the brain. Here we go. You're going to form this compound. And I guess I should have drawn my wedge coming out like this because this stereocenter is not affected. Like that. And there you go. Sulfur, methyl, and you're done. So there's your final product. Let's try the next one. Same rationale. If I was to highlight this carbon in yellow and this carbon in green, you can see that the carbon in yellow is less sterically hindered, and so it's going to undergo nucleophilic attack by a hydrogen from the hydride. So the hydride ion is going to come in and it's going to do a nucleophilic attack. Keep in mind that this carbon already has 2 hydrogens attached to it. So you're just adding a third one. Let's draw both of the carbons. So I'm drawing, let me maybe highlight them. Like this is the green one. This is the yellow one. Now the yellow one has 3 hydrogens attached to it. And the green one has the methyl group coming out like this. And then you're going to have the alkoxide. And in the second step, you do the exact same thing. You treat it with water like this. And now you're going to have a proton transfer. I can draw that a little better. Proton transfer like this. And you end up forming this compound. I have a question for you. It's kind of a weird one. Are there any stereocenters in this molecule? The answer is no. There are no stereocenters in here at all. And since there's no stereocenters, there's no need to draw this as a wedge. Kind of pointless. So let's draw it just like this. It's just isopropyl alcohol. And then for the last one, same rationale as before. We have our nucleophile. We have this carbon in yellow and this carbon in green. It's going to attack the carbon in green because it's less sterically hindered. So we have our nucleophile attacking. Open the ring. We have our carbon-carbon bond. This is our carbon in green. This is our carbon in yellow. The carbon in green, we have the bond to the alkoxide going up like this. We have the aromatic ring going in the back. I'll just put pH for the aromatic ring. And then you have the ethyl group coming out here like this. And on this carbon, you're going to have the O-ethyl. In the next step, you treat it with water. And the water does the proton transfer. And you end up with your final product, which is going to look like this, where you've got your ether down here, your alcohol up here, your aromatic ring going in the back, and then you've got your ethyl group coming out here like this. And that's it. So again, all of these were just nucleophilic attacks. The nucleophile always attacked the less hindered carbon, and then you did a proton transfer and you draw the final product, and that's it. Strong nucleophiles, which is something we learned way back in files. This is something we learned in chapter 7. Do not require acid. No need if you have a strong nucleophile. It's just going to do its thing. What if we have a weak nucleophile? Well, when we have a weak nucleophile, we need acid to promote the ring opening. And you can see that we have a catalytic amount of sulfuric acid in both of these reactions. We have water and methanol. So weak nucleophiles do require acid. Right? Again, going back to chapter 7, water is a weak nucleophile and methanol is a weak nucleophile. So what's the first step in the first reaction? It's going to be a proton transfer. So we mixed sulfuric acid and water. The major acidic species that we're going to have is a hydronium ion. So we'll draw out the hydronium, and we're going to do the proton transfer onto the epoxide oxygen to render it more reactive. So now we've made our oxonium. We've got our methyl group coming out of here. We've got a methyl group going in the back. And we've got an ethyl group coming out in front. And now we have our weak nucleophile, which is water. So my question to you, my students, is if I highlight this carbon in yellow and this carbon in green, the water is going to attack which carbon? Keep in mind that this carbon is, this carbon is a tertiary carbon, and this carbon is a secondary carbon. The tertiary is more hindered, but which one would undergo nucleophilic attack? Does anybody have an idea? Yeah, it's going to be the yellow one. Thanks, Brianna. Why? Because electronic effects dominate. So I'll write down here, electronic effects dominate. And so our nucleophile is going to attack at the tertiary carbon like that, and it's going to open up this bond, and that's going to cause an inversion of configuration. So both of these groups that are pointing down, they're still going to be on the same sides of the ring, but now they're going to be going up. They're going to be pointing up now. So I don't invert the wedge to a dash and the dash to a wedge. That's not what I'm doing. You got to understand that if this is the plane right here, these guys are below the plane, and now they're going to be up here because the nucleophile is coming in from the bottom side. So what that's going to look like with our product, we'll start by drawing the carbon-carbon bond and highlighting these as yellow and green, respectively. So now the methyl is still going back, but now it's going up and back. And the ethyl group is still coming out in front, but it's going up and coming out in front. And I have my water molecule attached over here. Of course, it's got a positive charge on it. And then over here, I've got my hydroxyl for my alcohol, and I have my methyl group coming out of the page like this. So then you have one more proton transfer. So in the last step, water is going to behave as a base, and that base is going to pull a proton off of here like that, and that's going to give you your final product. So just redrawing the whole darn thing here. And we have our methyl group coming out. We have this methyl group going in back. We have this ethyl group coming out. And now we have our hydroxyl just like that. There you go. So now we drew the entire mechanism, and we're reminded that when we have a tertiary carbon, it is the one that's going to undergo nucleophilic attack. Let's try the next one. I'm going to switch over to a blank document so that we can give it the old college try here. And let's give it a shot. So I'm going to redraw the molecule here carefully. Got my three-membered ring like that. I've got my methyl group sticking out. And then I've got this five-membered ring. Oops. There we go. So it looks something like that. Now I'm going to go a little bit faster this time. We're treating it with sulfuric acid, H2SO4, and methanol, which is CH3OH. The major acidic species in solution is going to be protonated methanol. Let me just move this a little bit. So the major acidic species in solution would be this, methanol that's gained a proton, that. And so I'm going to do a proton transfer to render the epoxide more electrophilic. So now I'm going to draw my oxonium ion, put my positive charge. Still got my five-membered ring here, 1, 2, 3, 4, 5, and my methyl group coming out here like this. Now in the next step, my methanol is going to do the nucleophilic attack. Methanol is a weak nucleophile. I've got a tertiary carbon right here, and I've got a secondary carbon here. Electronic effects are going to dominate, and the nucleophile is going to attack at the tertiary carbon. So what that's going to do is in my product, still going to have this carbon-carbon bond, and this bond going down and out towards the viewer. But now my 5-membered ring is going to be pointing up because this is a backside attack. And so here's my 5-membered ring now, and then here is my oxonium from my weak nucleophile here. And then in the last step, another molecule of methanol is going to come along and behave as a base, and it's going to rip this proton off like that, and I end up with my final product. So I've still got my methyl group here, my hydroxyl here, my 5-membered ring looks something like that, and now I've got my ether over here like that. There you go. There's the whole mechanism a second time. Okay, with all that information in mind, there's a lot there. Let's go back to the slides, to our slide deck, see what remnants we have in here after all the nasty tricks my iPad pulls on me. And we were down here, we covered all this. And we were somewhere, where were we? We finished all those, we finished those. And now we're going to turn our attention to thiols and sulfides. And it says skip here, but you know, you should know what a thiol is. I'll just go over it quickly with you. If you have an alcohol, I think everybody knows what that is by now. But if you replace the oxygen of a thiol, or oxygen of an alcohol with a sulfur, then you have a thiol. Another name for a thiol is a mercaptan, and that comes from the fact that sulfur can form bonds with mercury, and so it can capture mercury, so we call it a mercaptan. Anyhow, kind of an interesting thing there. And another functional group that you should know is, I think that everybody here knows what an ether is. We talked about it enough today, an ether. And if you replace the oxygen of an ether with a sulfur, then you've got a sulfide. So yeah, thiols and sulfides are very stinky, very, very smelly chemistry, to the point where I think that if you're a professor, it's actually hard to get graduate students to do research in sulfur chemistry because, let's say you're doing a PhD, that means you stink for 4 years and there's not much you can do about it. Okie doke. Well, let's take another break, and then we'll come back and we'll talk about some synthesis strategies.